We continue our discussion on the calculation of the basic reproductive number. This is part 3, and we are now going to work out an example in which we will compute the next generation matrix and the um, eigenvalues of this matrix. The example for the application of this method to compute R naught, as the example is provided by an epidemic model that we call the SEIR model. We're saying in the title here that this includes vital dynamics because we had seen a previous version of this model in which mu um, is 0 or in which mu is not part of the model, but here mu denotes the rate of departure out of this population. In that sense, mu denotes the death rate. So out of every compartment S, E, I, and R, there is always a constant rate mu that is being subtracted, meaning that these are the rate at which individuals in every compartment are dying due to natural causes. Okay. Let's see. Then we also assume that the deaths, and this is an epidemic model that also is connected with that model for birth and death process. Here we have the deaths being constant out of every compartment, and then we assume that all birds, all arrivals into this population are susceptible. They're assumed to be susceptible in such a way that the term that appears here in the susceptible class denotes the new arrivals, the newborns, and they're all assumed to be susceptible. Okay, so this is very standard model. And the first thing we do is that we'd like to do the decomposition, in which we are going to choose, according to the status, which compartments are disease compartments. In this case, the E and I compartment are both compartments of disease. That defines the state variable x, and then the operator f, fancy f and fancy v, these operators have to be defined in a way in which we can write the differential equations for the disease compartments, so that, well, we'll see that in just 1 second. So here we write x as e comma I, meaning that x1 denotes e and x2 denotes I. And in this way, the dynamics or the model for x is written as f operator f minus operator v, meaning here is f, here is v. And with this formulation, we what we do next is to compute partial derivatives. So the matrix F is computed out of partial derivatives on the operator F. Let's take a look at that operator again. This operator, fancy F, is a vector. It has two components. The first of which is beta S times I over N. I is denoted here as x2. And what we do and would like to do is this first component is considered f sub 1. So we want to compute derivatives of every component with respect to x1 and x2. The derivative of this expression with respect to x1 will be 0. The derivative of this expression with respect to x2 would be beta s divided by n. The derivatives of the second component, they're both 0. So that's what leads to this 2 by 2 matrix. One thing to notice is that disease-free equilibrium here is 0, 0, x1 0, x2 0, and s equals n, and we evaluate this type of Jacobian matrix at that disease-free equilibrium, then we obtain this 2 by 2 matrix. For the other expression of the other operator, which appears here, this operator, we do their kind of the same calculations. For every component, compute the partial with respect to x1. The first partial will be kappa plus mu, and the partial of that expression with respect to x2 is 0, and for the second component we're going to obtain constants. And when we evaluate those derivatives at the disease-free equilibrium, then we obtain that the matrix is reduced to this. So we have derived for the SEIR model with births and deaths, we have derived the matrices F and V which are used to form the next generation matrix. Okay, so what we have to do, that is perhaps no easy or trivial step, is that now that we have the matrix V, which is given by this 2 by 2 matrix, we have to compute the inverse of that matrix. Okay, again, not a trivial step, and once we have that, we can multiply F times V inverse, and that's how we arrive at this expression. This is a 2 by 2 matrix, and what we will do next is to compute the eigenvalues of this 2 by 2 matrix. Okay, so we have we observed that for this matrix called the next generation matrix, the entry on row 1 column 2, that would be this entry here, sorry, this entry, beta over mu plus gamma, that entry 1 2 is the expected, is quantifying the expected number, the average number of secondary infections produced in compartment E by an individual in compartment I, and this production is over the course of the infection. Okay, remember the first row of this matrix is connecting back to the first state variable, which is x1, which denotes E. Now, the entry in row 1, column 1, that would be k kappa beta divided by quantity mu plus kappa times mu plus gamma. So that 1 1 entry denotes the average number of secondary infections produced in compartment E by an infected individual in compartment E. Okay, so that's a note there about the meaning of some of these entries. And so the eigenvalues of this matrix K are 0 and the entry on the 1 1 location. Okay, so it is also straightforward to notice that both of these eigenvalues have 0 imaginary part. They are what we consider real numbers. Precisely, they are either 0 or strictly positive, so it's not too hard to figure between these two eigenvalues what is the modulus. Modulus of 0 is 0, and the modulus of a positive real number is that real number. In this case, modulus reduces to be an absolute value, and to choose the one that is largest in modulus is also straightforward. That's what we want. We want the spectral radius of the next generation matrix, and that spectral radius is precisely this expression kappa times beta over both of these quantities. That will be what we consider the basic reproductive number for the SEIR model with viral dynamics. And remember, the meaning of this quantity is that we can establish, at least for this model, this is a simple dynamics, we can establish a threshold so that when R naught exceeds 1, then we will have what we consider an epidemic, and when it doesn't exceed 1, then the epidemic dies out. So this is what is illustrated, very straightforward. You can code this up in R using LSOTA, and you can choose parameters of, you can choose values of the model parameters such that R0, let's go back, you can choose values of kappa, beta, mu, and gamma such that these, when you plug them into this expression, they are greater than 1. And that's exactly what was done here, setting parameter values such that that expression exceeds 1. In this case is 2.2, and these are the numerical solutions of the SEIR model with births and deaths. You can see how all state variables here are settling into some equilibrium levels that are positive levels, right? So this is reminiscent, this is resembling a scenario that we would call coexistence, right? We have used that terminology before. Um, and what happens when this is the scenario in which the basic reproductive number exceeds 1, meaning that those that are infectious are capable of replacing themselves, they're capable of producing on average more than one secondary infection. But what happens when that quantity is less than 1? Here's another example. Values of parameters were chosen such that um, R naught is less than 1, then there is a complete failure on behalf of the infected individuals to keep up. And the infection dies off because it's never able to have that critical mass of infected individuals, so that transmission really quickly dies off. Just for an illustration, on this scenario illustrated here, the total population was chosen to be 10,000, and half of them were chosen to be susceptible, half of them were chosen to be infected, but that didn't matter because with parameter values such that R0 is less than 1, that infected population quickly dies off. This is the red curve in these numerical solutions, and basically entire population settles on the constant population size. You can also see how all these curves, E, I, and R, the green, the red, and the blue, they're all going to 0. So this here is precisely the case in which the disease-free equilibrium is stable. Okay, E and I are 0, and then solutions that converging, E of t and I of t are converging to 0, and S is converging to the value of n here that was chosen to be 10,000. Okay, so then this illustrates the role that plays R0 in a very simple model, and we have illustrated the steps for the calculation of this spectral radius of the next generation matrix, and this concludes our conversation on the calculation of R naught.